Hello, in this video we're going to begin talking about the conservation of linear momentum, and we'll keep talking about it throughout the rest of this chapter. So let's start with our momentum impulse theorem. That told us that the change in momentum of a system is equal to the impulse that acts on that system, and impulse was defined as the integral of force over some period of time. And when we say force, really what we mean here is the net external force acting on the system, everything acting on the system from the outside. Okay, and if our net force acting on the system from the outside is zero, which could be either because there are no forces or because the forces have all canceled out each other, if that is equal to zero, then the change in momentum of our system is equal to zero. And so those special conditions correspond to momentum being conserved. So we call that the conservation of linear momentum. Put another way, what that means is that the initial momentum is equal to the final momentum before and after any process where the net force acting on the system from the outside is zero. So for example, if we have two objects collide with each other, if both of those objects are our system, the forces of them acting on each other don't count here, only the outside forces. And if there's no outside forces, then the momentum of the system before and after the collision are identical. Now notice that these are vectors. Momentum's a vector, and so in practice what we would do is break this up into components. So we would say that the initial momentum in the x direction is equal to the final momentum in the x direction, and likewise the initial momentum in the y direction is equal to the final momentum in the y direction, and a z component if you want in 3 dimensions. We're not going to do anything beyond 2-dimensional collisions here, but everything we do would extend to 3. It would just be more work. Now, for the statement to be true, two things have to hold. The first is that the system has to be closed, and the second is that the system has to be isolated, just like we have in our title up here. Okay, so closed means that no particles enter or leave the system. So no mass is added or removed from our system. And isolated means that there is no net external force. That's the statement up here. Okay, so closed, that might be one that you're not really thinking would matter. But this would be the difference between, say you have a wagon rolling down a hill. Well, it doesn't even have to be on a hill, just a wagon rolling along the ground, okay? And then suddenly somebody jumps into the wagon. So there's someone leaping into or out of the wagon. If they did that, the speed of the wagon would change, and seemingly in violation of conservation of momentum, not really breaking any rules. It's just a matter of, well, the statements here aren't true because a particle has entered or left the system. So no statements like that. We can do those kinds of problems. We just have to be very careful about how we set them up. Okay. Another point to point out is that sometimes you have momentum being conserved in one direction but not the others. Usually when objects are fixed onto some kind of, say, track. So you have from above two trains on tracks here. And if the track forces them to go in a particular direction, that's an external force. Okay, and so in which case that might seemingly violate conservation of momentum, where we have these two trains heading right at each other at a bend. In that case, we can't really generically say that momentum is conserved in both the x and the y direction because this track here is applying an external force. We could define a direction along the track, and in that case the momentum is conserved along the track. It's just a matter of picking the right coordinates. So again, we don't want to use the wrong equations for the wrong setups. Okay, there are two types of momentum problems in general. two scenarios, really, I should say. The first type is an explosion, where one object breaks apart into two or more. The other type is a collision, where two or more objects run into each other, and they may or may not end up sticking together. Now, in an explosion, the kinetic energy is definitely not conserved. The kinetic energy of the system is definitely going to change as a consequence of exploding. What's happening is internal energy is being changed into, for the most part, kinetic energy when the object explodes. So the kinetic energy tends to increase in an explosion. Whereas in a collision, the kinetic energy may or may not be conserved. The case where the kinetic energy is conserved is called an elastic collision. Otherwise, the collision is called inelastic. So here, elastic doesn't mean stretchy. Here, elastic means that the kinetic energy is conserved. You could think of it as meaning bouncy. Bouncy things tend to have most of their kinetic energy conserved, or for our purposes, we will take the idealization that all of the kinetic energy is conserved. Okay, so let's do an example. I'm going to pause for a moment, write down the question, and then we'll work the example. Alright, so here's our question. We have a firecracker explode, and let's say it breaks into just two pieces. And we measure the velocity of one piece and find that it's going due north at 10 meters per second. We want to calculate the velocity of the other piece. Now, you might reason that if one piece is going north, the other piece is going south, and that's actually correct. But let's prove that that's true mathematically and prove that that's consistent with what we just wrote down for conservation of momentum. So let's make a sketch of our system. So we'll have our firecracker that's broken into two pieces. So we'll have one piece and another piece. We have stated in our problem that one of these is twice as massive as the other. So we'll say that one has a mass of 2m and the other has mass m, whatever m may be. And we have this top piece going due north at 10 meters per second. We'll define a coordinate system where north is the y direction and then x would be the east direction. We want to figure out what this velocity is. And like I said, we can reason that it's probably going to be south, but let's prove that that's true. So let's look at our components. We'll do our x component first. The initial momentum of our system has to be equal to the final momentum of our system in the x direction. This statement is true because we have set up a closed, isolated system, meaning that our system is the firecracker, whether it be a single piece or two broken pieces, and we haven't identified any external forces acting on this. If this thing were tossed up in the air and were subject to gravity, then conservation of momentum isn't going to apply as written. We'd have to be careful about how we defined our system. But this is just a firecracker. We're not worrying about friction or air resistance to gravity, just firecracker by itself. So I guess firecracker in space. So the initial momentum is the unexploded firecracker, which is initially stationary. So m times 0 is 0. The final momentum is going to be the velocity of the two pieces. So we'll actually have two terms here. The first term will do the top piece, which has no x component to its velocity, so its momentum is 0. And then for the second piece, we'd have m times the x component of v. Alright, and this is what tells us then that the x component of v here has to be 0. That's the only self-consistent answer. So just as we expected, the firecracker is not going east or west. Okay, so let's figure out how fast it's going south. So it's also true that momentum is conserved in the y direction. So the initial y momentum is equal to the final y momentum. We will again start with our firecracker not moving at all. And then we'll have two terms for the after the explosion. For the top piece of our firecracker, we have a mass of 2m times a velocity of 10 meters per second. For the other piece of our firecracker, we have a mass m and a velocity vy. So the solution to this would be to move, I guess this would be 20m to the other side. And say that that is equal to m times vy. These m's cancel out, so vy is equal to negative 20. This would be in meters per second, just like we had up here. And if it's negative, that means negative y direction, which means south. Okay, so the velocity v is going to be equal to 20 meters per second due south. So does it make sense that we got twice as much speed as opposed to the top piece? And if you think about it, the answer should be a very clear yes, because we have half as much mass. The product of mass and velocity has to be the same. So 20 up, 20 down, 20 up and 20 down added together is 0. We started with 0 momentum, we end with 0 momentum because we have 20 units of it up and 20 units of it down, so we still get 0. All right, we're going to talk about collisions, the other kind of interaction, in the next video. So I'll see you in just a moment.